Okay, in today's class we're going to continue our exploration of the discovery of the atom and the historical benchmarks. 20th century scientists deduced what the electrons were doing by using spectroscopic data. One of the more important discoveries they made was called the Zeeman Effect. It started off with the 4 spectral lines of hydrogen, which contains very fine lines upon closer inspection. And these lines are separated when the atom that's giving off the spectrum is placed within a magnetic field. So if you take a hydrogen gas and you ionize it, you'll see these 4 lines appearing at the different wavelengths. You get a purple line, a blue line, a green line, and an orange line. That's the typical spectrum of hydrogen when it's pushed through when it's aimed through a prism. It separates it out to that spectrum. And these are emission lines. But if you then subject the hydrogen gas to a strong magnetic field, and you take a closer look at one of these lines, you'll see that it splits into 3 lines. So I wrote that down. So many fine lines appear in the spectrum of hydrogen if a spectroscope with a sharper focus and higher resolution is used. Bohr's model of the atom is too rough to be able to explain this fine splitting of the energy levels, which proved to be due to the different spatial orientation of the orbitals. So for example, p orbitals are oriented along the x and the y and the z plane. So they're spatially, they're in different areas of the x, y, z coordinate plane. This is known as the Zeeman Effect. Later it was discovered that electrons have spin, which explained what came to be known as the anomalous Zeeman Effect. There was even finer splitting that took place when the magnetic field was even higher, that enhanced splitting it even more. The Zeeman Effect is now used as a way of measuring the magnetic field strength of stars. So the reason for the Zeeman Effect is due to the fact that it distorts, the magnetic field distorts the shape of the orbitals in different ways because they were oriented in space in different directions. So it results in a slight difference in their energy levels, and that creates an emission spectrum that has 3 distinct lines instead of 1. Moving on to the second board. Louis de Broglie drew a connection between matter and electromagnetic energy. He proposed what came to be known as the wave-particle duality of nature. He began by showing that if energy is equal to mass times the speed of light squared, Einstein's famous equation, but energy is also equal to Planck's constant times the frequency of electromagnetic radiation. So he equated these 2 quantities, the energy contained by matter and the energy contained by electromagnetic radiation. He set them equal to each other. He replaced the speed of light with a vector, the speed of a particle, headed in a particular direction. And he isolated for lambda, having replaced frequency here with the vector over the wavelength. And when he isolated lambda, he found that every particle can be thought to have a wavelength. So even particles of mass m and velocity mu, or velocity v, sorry, have a wavelength. For example, and we could take a hypothetical electron traveling at the speed of 2.19 times 10 to the 6 meters per second. Here's the mass of an electron. Here's Planck's constant. If you plug in all those values into this equation, you get a wavelength. So an electron traveling at a certain velocity has a wavelength. And this fact was exploited to make the electron microscope. You can focus beams of electrons to create a lensing effect that can magnify objects, and this can be exploited to get magnifications in excess of 1 million or 2 million. Whereas with light microscopes, you can't go higher than about 2,000 magnifications because the detail washes out at any higher magnification. So for a large, slow-moving object, wave properties can be discounted. However, for an electron or some other small particle, wave characteristics can tell us much about the behavior of the particle. We could point out that momentum, mass times velocity, is related to the wavelength of the particle, because since lambda is equal to h over nv, mv is equal to momentum, h over p, is relating to the wavelength. So the wavelength of any particle is proportional to its momentum. So up to that point in history, Newtonian mechanics was able to describe the behavior of particles at ordinary velocity. But what happens when particles start moving at close to the speed of light? And it is possible to accelerate electrons to within 99.999% the speed of light. And those are called relativistic velocities. When you accelerate particles to those high velocities, they have an enormous amount of energy, and they don't behave in the same way that particles moving at a classical, that Newtonian mechanics could normally describe. So quantum mechanics is used to describe the behavior of small objects near the speed of light, and is necessary to really understand the behavior of electrons, because the electrons in an atom are moving at relativistic velocities. They're moving at somewhere near 2/3 the speed of light. Werner Heisenberg was a famous particle physicist who came to the conclusion that there were limitations that were inherent to quantum physics, and that was that the position of an electron and its momentum, when multiplied, had to be a number equal to or larger than Planck's constant. So that put a lower limit on the accuracy with which you could measure the momentum of a very small particle. It's kind of like trying to find out where a marble is in a room. Suppose you have a very darkened room so that you can't see where the marble is, and the only tool you have to find out where the marble is a beach ball. So if you throw a beach ball at the marble and you hit the marble, you'll hear the marble rolling in the room, so it'll disclose the position of the marble. But now that you've hit the marble, it has changed position, so you no longer know where it is. By finding its position, you have now changed its momentum. That's what this equation translates to. Heisenberg was basically proving that quantum mechanical calculations are necessarily fuzzy. Small, when you get to the ultra small, there are no more sharp edges. Things are better described in terms of probabilities. And this, we're going to see this later when we try to describe the shape and the position of the orbits that electrons occupy, known as orbitals. Erwin Schrödinger comes around the scene at this time. He wanted to inject some mathematics and some rational conclusions into the problem, and he came away from it even more frustrated than he went in. In fact, he disavowed ever wanting to have been involved with the Schrödinger wave equation, which helped us understand the shape of the orbitals, but still did not give him the satisfaction he was looking for. He calculated the total energy of an electron in an atom using both the potential and the kinetic energy of an electron, and he discovered the equation was solvable with the greatest degree of certainty when certain integer values were used. Kind of like tuning a radio. You can tune a radio a little bit off, and you'll get a station, but you'll hear a lot of static. If you get the tuning on perfectly, you'll get the radio station much more clearly, but even then, if there's any interference, you might still get static. The analogy limps a little bit, but this is the idea. The Schrödinger wave equation had solutions that helped you understand where the electrons were, but they didn't give you specific positions. What they gave you was areas of probability. So the Schrödinger wave equation gave a satisfactory explanation for the spatial orientation and the shape of the electron orbits that came to be known as orbitals. 4 numbers arise which represent the solutions to the wave equation. They are n, L, m sub L, and m sub S. N represents the principal quantum number. L is the azimuthal, I believe it's called, so it gives you the shape of the orbital. M sub L gives you the orientation in space, and finally m sub S came to be known as the magnetic spin, because the electrons, although they're viewed as particles, it's maybe not completely accurate to look at them as particles, but if a particle which is charged is spinning, one way to imagine it is to see it as a charged particle that's spinning, you would quickly come to the conclusion that
two particles within the same orbital, say they're spinning in the same direction, they have a magnetic field oriented in the same way, they're going to repel each other. So one of the ways that electrons will diminish their repulsions within the same orbital is to spin pair. One to spin up and the other one to spin down. And like magnets, if you've ever tried to put two fridge magnets together, you see that they repel each other, but if you flip them, then they all of a sudden they'll stick. So it's not exactly the same idea with electrons, but it's similar. They spin pair within the same orbital because it reduces the repulsions between the electrons. And that's where the fourth quantum number came in.